We all wish that we could sometimes see into the future. Now, thanks to the latest data from ESA's star mapping Gaia mission, astronomers can do just that for the Sun. By accurately identifying stars of similar mass and composition, they can see how our Sun will evolve in the future. And this work extends far beyond a little astrophysical clairvoyance. Gaia's third major data release, DR3, was recently made public. It discloses a database of the properties of hundreds of millions of stars, including how hot they are, how big they are, and what masses they contain. Gaia takes exceptionally accurate readings of a star's apparent brightness, as seen from Earth, and its color. Turning those basic observational characteristics into the properties of a star is painstaking work. Orlagh Creevey, an astronomer at the Observatoire de la Côte d'Azur in France, and colleagues from Gaia's mission team extracted such astrophysical parameters from Gaia's observations. The team built on the pioneering work of astronomers at Harvard College Observatory, Massachusetts, in the late 19th and early 20th centuries. At that time, the astronomers studied the appearance of spectral lines, the dark lines that appear in the rainbow of colors produced when a star's light is split with a prism. They ordered the stars by the strength of these spectral lines and found that this order was directly related to their temperature. It was later discovered that the width of certain spectral lines was related to the luminosity and age of a star. Correlating these two properties allows every star in the universe to be plotted on a single diagram, known as the Hertzsprung-Russell diagram. An HR diagram plots a star's luminosity against its surface temperature and reveals how stars evolve throughout their long life cycles. While the star's mass changes little during its lifetime, its temperature and size vary significantly as it ages. These changes are driven by the type of nuclear fusion reactions inside the star. With an age of around 4.6 billion years, our Sun is currently in its comfortable middle age, fusing hydrogen into helium and generally being rather stable. That will not always be the case. As the hydrogen fuel runs out in its core and changes begin in the fusion process, we expect it to swell into a red giant star, lowering its surface temperature. Exactly how this happens depends on how much mass a star contains and its chemical composition. This is where DR3 comes in. Creevey and colleagues combed the data looking for the most accurate stellar observations that the spacecraft could offer. The team wanted to have a pure sample of stars with high precision measurements. They'd focused on stars with surface temperatures between 3,000 and 10,000 degrees Kelvin because these are the longest-lived stars in the galaxy and hence can reveal the history of the Milky Way. They are also promising candidates for finding exoplanets because they are similar to the Sun, which has a surface temperature of 6,000 Kelvin. Next, the team filtered the sample to show only those stars with the same mass and chemical composition as the Sun. Since they allowed the age to be different, the stars they selected ended up tracing out a line across the HR diagram representing our Sun's evolution from its past into its future. And it revealed how our star will vary its temperature and luminosity as it ages. This work shows that our Sun will reach a maximum temperature at approximately 8 billion years of age. Then it will cool down and increase in size, becoming a red giant star around 10 to 11 billion years of age. The Sun will reach the end of its life after this phase, when it eventually becomes a dim white dwarf. Finding stars similar to the Sun is essential for understanding how we fit into the wider universe. To identify these solar analogues in the Gaia data, Creevey and colleagues looked for stars with temperatures, surface gravities, compositions, masses, and radii similar to the present-day Sun. They found 5,863 stars that matched their criteria. Now that Gaia has produced the target list, others can begin to investigate them in earnest. Do all solar analogues have planetary systems similar to ours? Do they all rotate at a similar rate to the Sun? These are some of the questions that scientists want answers to. If we don't understand our own Sun, and there are many things we don't know about it, how can we expect to understand all of the other stars that make up our wonderful galaxy, says Creevey. Gaia's extreme accuracy has allowed the parameters of more stars to be determined more precisely than ever before. The Gaia mission has touched everywhere in astrophysics, says Creevey. But it will not only help illuminate the sun's past and future. It will ripple out to many other studies, allowing us to know better the galaxies whose light is the amalgamation of billions of individual stars. Thank you for watching. And don't forget to subscribe.